on, off, on. Simple voice commands, right? But here's the thing. A lot of videos you see online for AI voice control either rely on hidden third-party firmware, tools like Edge Impulse, or black box modules with limited documentation. Now these approaches do work, but they feel like Arduino of machine learning. You get results without really seeing how it all works. So in this video, we will get started with TensorFlow Lite for microcontrollers and run a real voice command model on the ESP32 completely offline. Namaste and welcome back to Avinashee Tech. TensorFlow Lite or LiteRT as it's now called comes with a basic example called microspeech. If you look into it, you will see that it detects two commands, yes and no. Now here's something important. A lot of modern hardware platforms come with AI accelerators and optimized firmware implementations to run these models efficiently. But I am stuck with an older ESP32 dev kit board here without any dedicated AI accelerator. So all the inference will run directly on the CPU. But for this demo, obviously we can still use the ESP32 optimized TensorFlow Lite example, which uses the ESP-NN library within. Just take a look at the timing difference with and without this library. It is really noticeable. The dataset we are using comes from Google, created by Pete Warden. It has grown over time to include 35 words, from digits to commands, and even fun words like Marvin, dog, and bird. The word on has almost 3,800 audio samples, each 1 second of duration. Similarly, word off has 3,700 such samples. There's also a mini version of this dataset available, which comes handy to speed up the training process. Alright, I've got the speech dataset zip file here with me, and you can see that each word or command has its own folder. Let's quickly go through it. First up, background noise. Here you will find different audio samples like dishwashing noise, running tap, white noise, and a few more. Now let's jump to the word on folder. I'll just pick a random sample and play it.
On.
Now the same for word off.
Off.
Nice. Simple short 1 second clips. Now jumping to VS Code. Don't worry, I'll make this quick and yeah, we will discuss this part in detail in a separate video. So we start with our existing ESP32 and ICS43434 MEMS mic project. And if you haven't seen the previous videos in this series, you can definitely check them out to connect the dots. Okay, first we have to add the TF-Lite component file and then build the project. This automatically pulls in the required dependencies, including TensorFlow Lite and ESP-NN inside the Managed Components folder. Next, I'll just have to copy all the files from the microspeech example and start with modifications. Add support for bulb control using GPIO. Modify our main function. Make some changes to existing mic I2S config. Replace legacy I2S function in TF-Lite file with our I2S functions. Clean up unused files and finally update CMake file. Now comes the most important part, the model. In the current model file, the model is trained to detect yes and a no. But we will modify the model to detect voice commands on and off, along with usual silence and unknown. That's it, keeping it simple for now, but practical. So we move to Google Colab, connect to a GPU, and get started. First, I'll replace the wanted words yes and no with on and off. Here, we are using the full speech data set, which means all the remaining 30 plus words will automatically fall into the unknown category. No hyperparameter changes for now. While trying to run, we were prompted with a warning and we will just ignore it and go with run anyway. Next, you can find options like audio preprocessing model and speech model architecture. We will leave them untouched as well. Additionally, you can find the file paths where files related to our model will be saved. After running this initial setup cells, we reach the training section. Now this step can take a few hours, So we have to make sure our system doesn't go to sleep and is always connected to a power source and a stable internet.
One eternity later.
Once training is complete, the model file gets saved in the file directory. Next, it is time to convert the model into a format that a microcontroller can handle. Just take a look that the float model is roughly 67 kilobytes while the quantized model is around 19 kilobytes. And interestingly, accuracy on test sample is almost same for both the models. And we go with the quantized version. In the end of this notebook, we make use of a Unix command to generate a C array from our model. Back in the collab directory, we can find model.tf-lite file. Let's just download it and open it up in Netron to visualize the architecture. You will see a simple convolutional neural network at the beginning, followed by a fully connected layer, and finally in the end we have a softmax layer with output size 1 cross 4. These four outputs correspond to on, off, silence, and unknown. There's also a model.cc file generated, and it is exactly what we will need for our ESP32 project. Let's open it up in VS Code, copy the model data, and replace the older model. Make a few small data type adjustments after copying, and that's about it. Let's now flash the code and monitor the output. There we go. We can see on and off being detected along with the detection scores and bulb status. Time to take a look at the hardware setup. So ESP32 is connected with the MEMS mic and that has already been discussed in earlier videos. I'll be simply adding a relay module whose trigger pin is connected to ESP32 GPIO2. Power pin V plus of relay is connected to 5V or V in of ESP32 and V minus is connected to ground. On the AC side, we have neutral from mains connected directly to the bulb. The phase from the main goes to the relay COM connector, and NO or normally open connector is connected to the other end of the bulb, thereby completing the connection. Note this is a live AC connection, so be careful unless, of course, you are this guy. With that said, once the connections are complete, the setup looks something like this, and I'm using a simple LED bulb for this demo. Let's test it out. On, off, on. Well, it was not always a success. Sometimes it failed too. Watch this. Off, 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 off. Of course, the result depends on your mic placement, distance from the mic, your voice clarity, and loudness. And of course, the model accuracy to detect the command. But yeah, what I found was that command on was much easier to detect than off. My guess is maybe due to the ending F sound, which is a bit softer in tone and difficult to recognize. What's your guess? Tell me in the comment section. And that's about it for this video. A simple offline voice control system built from scratch without hiding the complexity. If you found this useful or interesting, do like and share this video. And if you are into this kind of real engineering content, consider subscribing the channel. This is Avinashee Tech signing off.